Hello, this is Continuity Part 1, and I'm Dr. Joseph. So continuity is an important notion in calculus. Um, we've been talking a lot about limits. This is a concept that ties that into saying the limit exists and it is what you think it is consistently. So most functions that we look at are continuous, and it's a convenient property. And we first start by looking at it just at a single point, just like limits, and then we look at it over an interval. And in the next video, you'll talk about discontinuities, which are usually very isolated, just a few places. Most of the time, we want our functions to be continuous. Okay, so you may have noticed using the limit laws, they basically allow you to plug in the value you're approaching. And continuity is the mathematical property that tells us when plugging in A will give us the right answer. Here's the definition. A function f of x is continuous at the point A if the limit of f of x as x approaches A is equal to f of A. So that's a very compact statement, and it actually means quite a bit if you unpack it all. So let's do that. So in order for the limit, or sorry, for the function to be continuous at A, all three of these things must be true. That limit as x approaches A of f of x must exist. F of x must be defined at A so that I can plug A into the function. And the value of the limit must equal the value of the function. So three things must be true. So this is a rigorous way of saying that the function passes through this point here, A, f of A. In this case, it's 3, 2. And in this picture, if we look at the limit as x approaches 3, our y values are approaching 2. And 2 also is the value of the function because this dot is filled in. So the limit of f of x as x approaches A is equal to f of A, f of 3 in this case. So this function is continuous at 3, the x value 3. Okay. So let's translate this into sequences like we did with the definition of a limit. And I think this sounds very reasonable. So a function f is continuous at the point A if for every sequence of x values approaching A, the corresponding sequence of y values approaches f of A. And how you should think about this is that roughly speaking, whenever x is close to A, f of x is close to f of A. So you can think of this in terms of what points, what sequences of points are approaching, and that as my x's are getting close and close to A, my y's must be getting closer and closer to f of A. So here's a picture with a sequence of x values approaching A, which in this picture is the number 3. And f of 3 is 2, because we have this point 3, 2. And we can look again at the corresponding y values and see what they're approaching. They're approaching 2, which is equal to f of 3. So this is one sequence of x is approaching A and the y's are approaching f of A. Of course, we need to check that for every sequence for it to be continuous, but this is how you can mentally look at a graph and think about, is it continuous at this point or not? Okay, so to check this graphically, we want to look at the limit as we're approaching the point in question. So the question was, is this function continuous at 3? So we're always talking about x values when we say where. So we need to look at this limit, f of x, as x approaches 3. That limit, well, we can look at the two one-sided limits from the left. My y's are approaching 2. From the right, my y's are approaching 2. So the limit is equal to 2. The only thing left to check continuity is 2, is the limit of that was 2 the same thing as f of 3? And yes, it is. F of 3 is equal to 2, again, because this dot is filled in. That's what I'm checking graphically. So that was continuity at a point, and now we want to expand that to continuity over an interval. So this is the open interval from A to B, meaning I'm not including the endpoints. And we're continuous over that interval if we're continuous at every single point in that interval. Now, again, that seems crazy. How could I possibly check this definition that took several things to check at every single point, right? Well, that's the way it is, but we don't have to check it at every single point, and we'll see how we're going to build that up in the next few slides. Also, one of the endpoints or both could be infinite, and we do have a notion of continuity on a closed interval, which is going to be really important fairly soon. So what do we do with the endpoints is basically what we need to know. On the interior points, it's just the same as what we already said. And then at the endpoints, let me actually write in the pen here. So if here's A to B, we want to be right continuous at the left endpoint, meaning we just look at the limit as we approach A from the right. Is that equal to f of A? And same thing at the right endpoint here. We're asking about the interval A, B, so it only makes sense to approach it from the left and ask, is that left-hand limit the same as f of B? So let's just do an example or sort of a definition check. What does it mean to say f of x is continuous on the interval from minus infinity to infinity? Well, you're supposed to think about that, but I'll give you the answer. It means f of x is continuous at every real number. Okay, 2, a little bit trickier. Over what intervals is this function, graphed in red, continuous? So here we want all of the intervals, and essentially what you will end up doing is looking for discontinuities. That'll be discussed in the next video. So right now, we're just trying to think, is f continuous at this point? Yes, it is. Is it continuous at this point? Yes. It's continuous at all these points. Where is it not continuous? This is one point, or the x value being 2 is one point where it's not continuous. And also this x value of 5. And you'll learn more about the different types of discontinuities in the next video, but I claim it's continuous everywhere else, and you can think about that. But if you believe me, the way you write that down is using interval notation. So we can say it's continuous from minus infinity all the way until 2. And then I want to tack on another interval from 2 until 5. And then tack on another interval from 5 until infinity. This U symbol means union. It just means it's continuous on these intervals. Okay, so that would be the answer there. And when you're evaluating problems like this, it's best to just put the open interval. We'll talk more about continuity over a closed interval once it actually sort of matters, which won't be for a couple of weeks. All right, so here's where we start to get to the good part, where we get to say, actually, most of the functions we care about are usually continuous. Or oftentimes we'll say they're continuous on their domains. And so this is great because then if we want to know what's the limit of this function as I approach some value, all we have to do is plug in that value. So for example, polynomials are going to be an example of functions that are continuous at every real number. So if I have a polynomial like this one, and I want to know what's the limit as x approaches 2, all I have to do is plug in 2. Just evaluate the function at that x value, and that's the limit. So here's a long list of common functions that are all continuous, where they are defined. So polynomials, we already said. Rational functions. Now, some of these aren't defined everywhere. So example, if you have like 5 over x minus 3, this is not defined when x is equal to 3. So this would be continuous everywhere except 3. We'll get into that with the examples too. Root functions. So if you have like square root x, for example, you need x to be greater than or equal to 0. Trig functions, and then exponential and logarithmic functions. Okay. And another great thing is that if you have two continuous functions and you combine them in a simple way, what you get is usually also continuous as long as you can plug in those points. So sums and differences, constant multiples, products and quotients, again, as long as we're not dividing by 0, powers, roots, and this last one is especially important. Compositions of continuous functions are continuous where they're defined. Okay, so that was kind of a lot. So let's do some examples. Here's a rational function. Where is it continuous? Well, since it is a rational function, that previous slide tells me that it's continuous on its domain, which is everywhere except -5. Can't plug that in because I'll get 0. So this is continuous from minus infinity to -5, and then also from -5 to infinity. So everywhere except -5. And this is the same as just saying for all x not equal to, oh, that should be -5. But we will generally ask you to give your answer in interval notation. So you should get into the habit of doing that. Okay, so we've already sort of said this, but now that we know that this is continuous, it's super easy to evaluate a limit. If I want to know what's the limit as x approaches 7 of this function, well, since I've already justified that it's a continuous function, all I do is plug in the value I'm approaching, f of 7. And that's it, piece of cake. Example 2, what's the limit of sine of square root x as x approaches pi squared over 4? Okay, so that seems like a pretty weird thing to be asking. I wouldn't really know how to do it unless I knew these facts we just discussed. Sine functions, square root functions, they're both continuous. So their composition, sine of square root x, is also continuous. And so again, I just get to plug in the value. First, notice this is part of my answer, is justifying that this function is continuous by showing it's a combination of continuous functions. But once I've done that, I'm allowed to just plug this value in for x. So the answer is sine of the square root of pi squared over 4. And if you want to simplify that a little bit, the square root of pi squared over 4 is pi over 2, because it's square root pi squared over square root 4. And so the answer is just sine of pi over 2, which is equal to 1. Okay, here's a try it yourself. A piecewise function where the definition of the function changes at 4. And the question is this function continuous over the closed interval from 0 to 6? So here you have to check continuity over the open interval from 0 to 6. And then you have to check, is it right continuous at 0 and left continuous at 6? The answer is yes. There's several things to check besides what I just wrote down. You have to also check something about what's going on at x equals 4. So you might want to make a sketch, but try to write down a complete argument. All right, so making connections, most real-world data is fairly well modeled by continuous functions because small changes in the independent variable usually produce a correspondingly small change in the dependent variable. And also on a technical note, most of what we'll do in calculus requires our functions to be continuous. So going back to this chart we had a while ago, try to think about these relationships between these variables, which seem like they could be continuous. Do any of them seem like they might not be? And this is where interpreting a model, the context starts to matter. So in abstract math land, functions can go up and down very fast, very far, very quickly. But in context, that probably doesn't make sense. So one example could be like the stock market. Something changed very quickly there. I think an even better example, going off this last one, time and velocity, is a baseball that's being thrown by a pitcher at 100 miles an hour. It is moving quite fast, and then it hits the catcher's mitt and stops very quickly. And if you look on a micro time scale, it is decelerating continuously to a velocity of 0. But on any normal time scale, like seconds, this would seem like really fast and then instantly just 0. And so that's going to be, in a reasonable scale, it's going to look like a discontinuity. So context matters here. But most things, unless they're undergoing really sharp, jagged changes, will be continuous most of the time. And that means they're actually very useful for modeling real world situations. All right, great. And next time, get ready for some discontinuities. All right.